Okay, good afternoon, ladies and gentlemen. This is Professor David J. De Los Reyes. It's October 1, 2024, and the time is 15:10. It's 3:10 p.m. Okay, my topic will be a long video format. We haven't had a long video format for a long time. So for this afternoon, I will be discussing the continuation of one of my long video format topics, DC circuit. Okay, let's proceed. The title of the topic for this afternoon will be, it's a long video format topic, a continuation of my DC circuit. And on DC circuit, I am now on lesson number 19. We are running smooth. We are studying the different concepts gradually, so we could tackle it all for those who will be taking up electrical engineering. Okay, the title of the topic will be DC circuit, lesson number 19. Okay, under the subtopic superposition theorem example. Meaning to say, I will be giving an example problem on superposition theorem concept. The last time around, I discussed the solution of a current using superposition. Okay, I've just given you two voltage sources. So for this afternoon, I will be giving three voltage sources. Okay, the last time around, we got two. But for now, I will be giving you example problem if the number of voltage sources is 3. So the given figure here, we are given a 24, 18, and 12 volt battery or a direct current source. Okay, supplying current to a load RL 16 ohms. Okay, so with this given configuration, meaning they are all in parallel, okay, the problem is asking what will be the total current passing through the 16 ohm load. Capital letter I with the subscript 16, again with the subscript T, that T refers to the total current. Total current meaning the total current coming from the 24, 18, and 12. Okay, let's proceed. The concept for a superposition theorem is that to solve for the current that was delivered by a certain voltage source, we will consider each voltage source at a given time. We will short the other two to compute for the current emanating from it. So for the solution, we'll try to consider the 24 volt source. Okay, superposition. Meaning to say, we disregard the 18 and the 12 volt, and we'll try to compute for the current coming from this. That will be delivered to the 16 ohm load. Okay, but we must have to take into consideration the internal resistances by the two other voltage sources. So for step number 1, we will consider the 24 volt source. So the configuration will be this. We maintain the 2 ohm. We maintain the 3 ohm. This is the 16 ohm load. For the meantime, we are considering the 24 volt source. So this will be the configuration. So with this given configuration, if we try to disregard 18 and 12, what will be this current here? Okay, and to solve for this current, of course, we will be using our knowledge of the so-called series parallel concept. Since there is only one voltage source, okay, we'll try to compress first all these resistances into one, so we could compute for the total current. And upon the computation of the total current, we could go for the computation of the I-16. So the key to the solution is actually our knowledge of the so-called simplifying of certain parts of the circuit if it is series or parallel. So if we try to simplify this one, these 2, 3, and 16 are all in parallel. So if we try to take the compressed equivalent of this one, I will be representing that one by RE. Oh, I could place a subscript number 1. Okay. There are 3, right? So 1 over RE1, the equivalent of that one will be 1 over 2 plus 1 over 3 plus 1 over 16. Like from the previous discussion, if there are only 2 resistances, we could compute for RE1 directly by taking the product all over the sum, but since there are 3, okay, so it will just be simply 1 over 2 plus 1 over 3 plus 1 over 16. We are not on the topic algebra, so I performed this one already by using the calculator. And the single equivalent of this one will be 0.896. So RE1 now will be the reciprocal 1 over 0.896, and this is 1.16 ohms. Meaning to say, the single equivalent of this one is 1.16 ohms. Okay, so we simplified this 3 here. To conserve space, I don't want to draw again the next figure, because the next figure will be this 24 volt in series with this 1 ohm plus the single equivalent of this 3 here. So I place it here. Capital letter R with the subscript T, again with the subscript 1, will be 1 plus the single equivalent, 1.16, and that will be 2.116 ohms. Right? So we are now given a circuit in which the total resistance is 2.116, and we are given the applied voltage to be 24. So this capital letter I with the subscript T, subscript number 1. Okay, will be the applied voltage all over the compressed equivalent of this one, and the compressed equivalent is actually 2.16, and what will come out will be 11.34 amperes. So in here, there will be a current coming from voltage source 24 volts. What's the value? 11.34 amperes. Okay. So to compute for the current passing through the 16, this 1 ohm, these 2 ohms, 3 ohms, 6 and 16, they are all in parallel. So I designated the voltage across these. Okay, the voltage across these 2, 3, and 16 are the same. So if we know the total current, we will subtract the voltage drop across this 1 ohm load here, and we could compute for the voltage across AB. And I place it here. The voltage across AB is actually the same as the voltage across the 16 ohm load. Okay, so it will be 24 minus the drop here, 11.34. The resistance is 1 times 1. And if we try to subtract, 12.659. So it seems there is a voltage here of 12.659 across this. Same as this one, same as this one. Okay, so if we know the voltage across the 16 ohm load, okay, we could compute for the current passing through it, given by the 24 volt source. So I place it here. It will be 12.659, the voltage across the 16 ohm load, all over 16, and what comes out is 0.7912 amperes. So meaning to say, the current passing through the 16 ohm load due to the 24 volt source is 0.71912 amperes. That is part of the total current passing through the 16 ohm load, because we got 2 more voltage sources. So to continue the solution, let's try to consider the second voltage source, the 18 volts. Right? We are done with the 24, so we'll consider 18. So we short out the 24, we short out the 12, and again, it's the same as from the first part of the solution. We'll try to compute for the current passing here due to the 18. It's the same procedure, so the configuration will be this. We short out 24, the internal resistance 1 ohm remains. This is the voltage source that is being considered. The internal resistance is 2 ohm, the voltage is 18. We short out the 12 volt source, but we consider the internal resistance of the 3 ohms. So 3 ohms is still in the figure. This is the 16 ohm load. Okay? Again, to compute for the total current, okay, we simplify this 1, 3, and 16. If we try to rearrange, actually, we could place the other. We remove this one, so it will look simplified. This is 1 ohm. Okay, so if we try to take for the total current, we must have to take first the single equivalent of this one. Okay, single equivalent. They are in parallel. These 3 here, 16 and 1 in parallel. So 1 over R8, this will now be subscript number 2. We are considering R8. So it should be 1 over 1 plus 1/3 plus 1 over 16. And if we try to take the I didn't place the complete simplification. What comes out for R8 will be 0.7164 ohms. And this single, this is 0.7164, right? So if we try to compute for the total resistance now, it will be the single equivalent plus 2. So I place it here, the RT with the subscript 2 now will be 2. The internal resistance of the 18 volt plus the single equivalent of this 3 here, 0.7164. So what comes out is 2.7164. So it seems you are given a circuit in which the applied voltage is 18 and the total resistance is 2.7164. So the total current will be 18 over 2.7164, and this is 6.626 amperes. So this value here is 6.626 amperes. And again, I mark this one as terminal A, terminal B, because I want to show that the voltage across the 3 ohm, 16 ohm, and 1 ohm are all the same. So I could just designate that one as simply the voltage across AB. And that voltage across AB is the same as the voltage across the 16 ohm load. So I place it here. The voltage across AB, am I still on camera? Yeah, I am still on camera. It's actually same as the voltage across the 16 ohm load. So it will be the total 18 minus the voltage drop here. The voltage drop here will be 6.626 times 2. 6.626 times 2. So the voltage drop across the terminal AB is 4.747. This is 4.747, 4.747, 4.747. And we are interested in the voltage across the 16 ohm load. Since they are all in parallel, like what I said, it is 4.74 volts. So to compute for the current passing through the 16 ohm load due to the 18 volt source, it will be 4.747, the voltage across it, over 16, and that will be 0.2967 amperes. That's a part of the current passing through the 16 ohm load. Okay. Let's try to consider the third voltage source. We'll consider the 12 volt source. So we short out the 24, we short out the 18, but 1 ohm and 2 ohms will remain. So the resulting configuration will be this. The internal resistance of the 24 is 1 ohm, it remains. The internal resistance of the 18 volt source is 2 ohms, it remains. We are considering the 12 volt source, the third one, and this is the 16 ohm load. So actually, this 1, 2, and 3, 16 are all in parallel. So to compute for the total current coming from the 12 volt source, we must have to simplify first. Okay? Actually, we could place, so we could visualize more easily. This is 16. We replace 16 here. I will remove 16 here. I just transfer it, right? Okay? So if we try to take this total current, we must have to take the simplified equivalent of this. They are all in parallel. So 1 over RE3 now, I will place a subscript 3. Should be 1 over 1, 1 over 2, plus 1 over 16. They are in parallel. 3 resistances in parallel. So the simplified equivalent, I didn't put the complete simplification. What comes out is 0.64. Right? So our total now will be the single equivalent of this one plus 3. So our total will subscript 3 now will be 3 plus the single equivalent of this one, which is 0.64. So we are now given a simple circuit in which the voltage source is 12 and the total resistance connected to it simplified is 3.64. So the total current coming from the 12 volt source will be 12 over 3.296. Oh, this is 3.296 amperes. Right? So if we try to compute for the current passing through the 16 ohm load, I mark this one as A, this is B, this is still A, this is still B, this is still A, this is still B. Okay? So actually the voltage across the 16 ohm load is the voltage across AB, and that will be given by this one. It will be the 12 volt source minus the drop here. The drop here is 3 total resistance here times the total current is 3.296, and what comes out is 2.11. So the voltage across this AB here, which is the same as the voltage across the 16 ohm load, okay, is 2.11. We will, if we try to compute for the current now, it will be the voltage across this, which is 2.11 over 16, and that will be 0.1318 amperes. That's the third current passing through the 16 ohm load due to this 12 volt source. Okay, so actually there are 3 currents here. The current given by this one, the current given by the 18 volt source, and the current by the 12 volt source. And we have already computed the individual currents due to this. So to compute for the total current passing through the 16 ohm load, with the simultaneous application of the 24, 18, and 12, it will be the summation. It will just be simply the first current 0.7912 due to the 24 volt source, and the current due to the 18 volt source is 0.2967. Where's it? This one. Right? So this is 0.2967. And the current due to the 12 volt source is 0.1318. It is just the summation. We are on this circuit, so we are adding real numbers. There is no, it's not a complex number. So the total current, I with the subscript 16, again with the subscript capital letter T, meaning the total current passing through the 16 ohm load due to the 3 voltage sources will be the summation. And what comes out is 1.2197 amperes. Okay, that's it, guys. That's how to compute for the current on a certain part of a circuit with the simultaneous application of 3 voltage sources. This application, this problem comprises of 3 voltage sources. Okay, good afternoon from Los Angeles, Professor David Jedler.